Welcome to the Mathematics of Thinking. In this playlist, we'll be diving into famous variety of algorithms. We'll be breaking them down into visuals and in order to understand how they empower every tool we use every single day as a data engineer. So yeah, let's get started. So far in this series, graph traversal, shortest path, probability, random simulation, and dynamic programming optimization. Today we shift into signal processing, and I promise this is one of the most beautiful algorithms in all of computer science. Today, the fast Fourier transform, I am going to show you how any complex signal, whether it's audio, stock prices, sensor reading, brain waves, can be decomposed into its pure frequency components in O of n log n time. By the end of this video, you will understand why your phone runs this algorithm thousands of times per second, and yeah, you probably never knew. Imagine yourself trapped in this situation. You are working with a sensor data from an industrial machine. Every second you get a stream of vibration measurements. The signal looks chaotic, noise, jagged, irregular, hard to interpret. But buried inside the signal are patterns the machine runs at a domain frequency. There might be a new vibration appearing in an early warning of mechanical failure. The noise from the environment is at different frequency. You cannot see any of this staring at the raw time series. The patterns are hidden. How do you unmix them? How do you look at this chaotic waveform and instantly know which frequencies are present, which are dominant, and which one just appeared 2 hours ago and should not be there? The answer is the fast Fourier transform, and it does not just work for sensors, it works for audio, images, communications, finance, any signal where the underlying frequencies matter. So before we look at the algorithm, I need to give you the most important conceptual shifts in signal processing. There are 2 ways to look at any signal. The time domain, this is the raw data amplitude on the vertical axis. Time on the horizontal, this is what your sensor records, what your microphone picks up, what your stock price feed delivers. Look at the left panel, a wave plotted over time, it's oscillated. You can see it goes up and down, but you cannot tell which frequencies are in it. It just looks like a wave. The frequency domain, this is after the FFT amplitude on the vertical axis, frequency on the horizontal. Suddenly you can see spikes at specific frequencies. Look at the right panel, same signal, but now you can see dominant spikes at 20 Hz and 100 Hz. The rest is small noise. The FFT is mathematical bridge between these 2 views. It takes you from time domain to frequency domain. It answers the question, given this complex waveform, which pure sine waves would you need to add together to recreate it. Time domain shows you what happened, frequency domain shows you why. This is the difference. The mathematical operation we want, called the discrete Fourier transformer, stands for the DFT. It takes n time domain sample and produces n frequency domain values. The problem, the naive DFT algorithm, is O of n squared for every output frequency, k. You multiply the entire signal by a complex exponential and sum all n values. Repeat that for every k. You get n times n operations. Look at the left panel, 1024 samples, 1 millisecond fine gives like 1048576 samples, 17 minutes, and usable. 16 million samples, 7.5 days, completely impossible. So Cooley and Tukey in 1965 had the insight that changed everything. They realized you do not need to recompute everything from scratch. You can split the signal into even and odd indexed samples, computed the DFT of each half recursively, and combine the two results in using a simple operation. This divide and conquer insight reduces O of n squared to O of n log n. Look at the right panel now. We have 1024 samples, 0.01 milliseconds, 1 million samples, 0.2 milliseconds, 16 million samples, 3.2 milliseconds. The same mathematical result, 1000 times faster. This is why the A50 is called one of the most important algorithms discovered. So the Cooley-Tukey algorithm. So let me explain how the A50 actually achieves this speed up. Three concepts: divide, conquer, butterfly. Divide, take your endpoint signal and split it into two halves. Even indexed samples go into one array, multiply 0, 2, 4, and so on. Odd indexed samples go into another x1, extra, multiply by 1, 3, 4, 5, and so on. Two arrays of n over 2 points each. Then conquer, compute the A50 of each half recursively. Each half problem is half the size. The half splits again into quarters. The quarter splits into 8. This continues until we hit n equals 1, where A50 of a single sample is just the sample itself. Then butterfly, this is where the magic happens. After computing the two half A50s, we combine them using the butterfly operation. For each output pair, we take one value from the even A50 and one from the odd A50, multiply the odd by twiddle factor W, which is a complex exponential, a rotation in the complex plans, and add them for one output, subtract for the other. And look at the butterfly diagram at the bottom. Input a form even input b from odd, multiply by the twiddle factor W output, a plus W times b and a minus W times b. This pattern is applied at every level of the recursion. Log 2 of n levels total each with n operations, total n times log n. So let me trace through a real example. So as an input, we have a signal sampled at 100 hertz, 100 data points over 1 second. It looks like noise, but we know it contains two sine waves, 15 hertz and 120 hertz, buried under random Gaussian noise. Split, we divide the 100 sample into even indexed and odd indexed array, 500 points each. Recurse, we apply the A50 recursively to each half splits again and again. Log 2 of 1,000 is approximately 10. So we go 10 levels deep before hitting equals 1. Butterfly at each level coming back up. We combine the two sub FFTs using the butterfly operation with the appropriate twiddle factor. Total operations 100 times 10 equals 10,000 compared to the naive DFT. 1,000 times 1,000 equals 1 million. The output, the FFT produces the frequency spectrum. Two dominant spikes appear at the exactly 15 Hz and 120 Hz. The noise, which was uniform in time, spreads out in the across all frequencies at low amplitude. Then we have the filter. We apply a threshold. Any frequency component with amplitude below our threshold gets zero out. Then we run the inverse FFT to go back to the time domain. The result, a clean signal with both sine waves preserved and the noise eliminated. So signal to noise ratio goes from 12 dB before to 48 dB after the FFT filter. That is extraordinary improvement. So here is the full pipeline in NumPy, 5 steps. Step 1, we generate our test signal. We set the sampling rate to 100 Hertz. We create a time array of like 1,000 points over 1 second using NP line space. We build the signal as two sine waves of 17 and 100% amplitude at 15 and 120 hertz plus random Gaussian noise. Step 2, we apply the E50 np.fft.ft takes our signal and returns complex numbers. np.fft frec generates the corresponding frequency axis. np.abs gives us the amplitude at each frequency. Step 3, we find dominant frequencies. We set a threshold here 100 and extract all frequencies where the amplitude exceeds it. Running this will print exactly 15 and 120. Step 4, filtering. We copy the FFT result. We zero out all coefficients where amplitude is below the threshold. This is the core of low pass and band pass filtering. And step 5, inverse the FFT and FFT.EFFT, it means stands for inverse, transforms our filtered spectrum back to the time domain. We take the real parts, the imaginary components are floating, point noise effectively zero. This is the entire pipeline: FFT forward, analyze, filter, FFT backward. In production, you would wrap this in a streaming processor and run it on incoming sensor data in real time. Where FFT lives in the systems you use every day, we have the audio compression, the MP3. When you play an MP3 file, your phone decodes audio that was compressed using the FFT. The audio was transformed to the frequency domain, frequencies the human ear cannot hear above 20 kilohertz, and masked ones were discarded. The result is stored. That is where the multiplied 10 times the size reduction comes from. Then we have the medical ECG and EEG. Cardiologists use FFT to detect abnormal heart rhythms by looking at the frequency spectrum of an ECG signal. EEG brain scans use it to decompose neural activity into alpha, beta, theta, and delta waves, each associated with different brain states. We have finance, we have 5G wireless, OFDM, orthogonal frequency division, multiplexing. The technology underlying LTE and 5G is built entirely on the FFT. Your phone encodes data across hundreds of sub-queries, and your baseband chip runs FFT thousands of times per second to encode and decode your calls and data. We have IoT, LEGO, the gravitational waves. The Nobel Prize winning detection of gravitational waves in 2015 used FFT to extract a 0.2 second sharp signal from miles of detector data contaminated with seismic noise, thermal fluctuation, and electromagnetic interference. FFT found the signal that confirmed Einstein's prediction made 100 years earlier. Two numbers again: time complexity O of n log n, Cooley-Tukey radix minus 2, n must be a power of 2 for this exact complexity. Pad with 0 to the next power of 2 if your signal length is not. For the space O of n, the output array is the same size as the input. M-place variant exists for embedded systems. 3 limits. First, power of 2 constraints. Cooley-Tukey FFT is optimized for n equals the power of 2. If your signals had 100,000 samples, pad it to 124 before applying FFT. Second, the Nyquist-Shannon sampling theorem. You must sample at least twice the frequency of the highest component in your signal. If you sample at 100 hertz, you can only detect frequencies up to 500 hertz. The Nyquist frequency, any frequency above that will alias and disappear and appear as a false lower frequency. This is fundamental and non-negotiable. The third thing is complex outputs. np.fft returns complex numbers. np.ibs gives you the amplitude at each frequency. NP.angle gives you the phase. For most applications you only need the amplitude, but the phase encodes timing information, critical signal reconstruction, and correlation. So four things you now know. One, the FFT decomposes any signal from the time domain into the frequency domain, revealing which frequencies are present and at what amplitude. Two, the naive DFT is O of n squared. Kolituki uses divide and conquer, split, even, odd recurse combined with butterfly, achieving O of n log n. 3, numpy np.fft.fft gives you the full pipeline, transform, inspect the spectrum, filter by zeroing coefficients, reconstruct with npfft.efft, and used everywhere. The fourth thing that we know now is that used everywhere: mp3, audio compression, 5G, wireless communication, ECG and EEG, medical analysis, quant finance, cycle detection, IoT, anomaly detection, and the gravitational wave detection at LEGO. And yeah, so drop a like if this was useful, and tell me in the comments which application surprised you the most. The LEGO gravitational wave story always gets people. So in the next episode we'll be talking about MapReduce, how Hadoop counts 1 billion words across 1,000 machines. We go from signal processing to the distributed computing, and I will show you how the same map and reduce idea that Hadoop uses appears everywhere in your data pipeline. So see you there. By the way, if you are new to Python, I'm launching a Python information. You can subscribe by filling the form in the description.